Homework questions or anything?
Can we go over number 5, part B,
Yeah.
from the program or something similar?
Oh, okay.
Did we have a homework?
Not a daily homework. No.
Okay, so
I
you
had
have one
a
for
question on like 5B for the weekly assignment. It's on the electrical power required for turbine.
Okay.
Actually, it wasn't there, but I was thinking of it as a problem.
we needed to convert the CV to CP, right?
I don't remember the problem yet.
Can we do the full problem 5 then? Please?
Well, yeah, I mean, I can talk about it a little bit. I'm not going to do the whole problem, but okay, so we got a compressor. It gives you a pressure and a temperature at the inlet, temperature and pressure at the exit. So you can find any properties you want at the inlet or the exit. It's air. Probably that means use the ideal gas law.
We can still use like the website though for as dry air as the one of the things we can.
Yeah, you can. I'd say whenever I say air, pretty much, I'm thinking of you using the ideal gas law. Okay, so and we have speed at the exit. Well, so for part A, if you set up the first law for control volumes, you can figure out what the H's are at the inlet and exit because you have all the other information. And you're ignoring, kinetic and potential. So you're getting rid of all the V's and all the Z's in the first law. But okay, it's steady state, so you know that the mass flow rate is the same at the inlet and the exit. And so you can look up the specific volume at the inlet and the exit, and then you can use the equation for the mass flow rate to find the speed. So I guess that's the way to do part A. Are you with me on part A? Anyone? Why isn't this showing up on computer? Okay, so you cancel everything, but enthalpy and does it say anything about heat transfer? Okay, so the first part, I guess you don't even have to use, for part A, you don't even have to use the first law yet. You can just set up that m dot is equal to A times the speed divided by the specific volume and just calculate the speed that way. Yes, exactly. So you have everything you need to calculate m dot at the exit, and then you know that that's also m dot at the inlet because it's steady state, and then you can calculate the speed. Okay, so now you go to the first law for part B, and it gives you that Q dot is 500 times 10 to the third watts negative. And you already have all the other information. And so The only thing that you don't know there is W dot, and you can calculate that.
What I use as a formula, just W dot CV is equal to U dot plus M dot times the difference of specific
Mm-hmm.
entities. And it just didn't seem like what was the other piece of information? Like well, no, CD was relevant for that since we already had the information they had. It's just
If you're using the if you're just using the website, then CV isn't relevant. But if you're using uh, the ideal gas assumption, then you can calculate the change in. It doesn't seem relevant, does it? Because
Yeah, because you can get the enthalpies for both before and after.
yeah.
Yeah, 'cause that's where I got stuck.
Okay.
I feel like I was
You're
like,
just
I was like, I think I have to use this. So
okay. I will say that on problems that I use from the textbook loves to, the one that I was using, loves to throw unnecessary information into problems. So you have to kind of pick and choose what you need and what you don't need. So yes, I really don't see why you would need to know that.
So should we be studying how to do that for the exam, or you don't think you'll
How to do
like how to break down like CV and
oh, okay. Well, yeah, let me talk about that for a second. So just remember that for ideal gases, so if I start with the definition, CV is equal to partial of U with respect to temperature at constant volume. Um, let's see. Well, we know that for an ideal gas, U is only a function of temperature. And so CV just turns into du dt. And so du is equal to CV dt. And you can integrate both sides. So that works the same as for a liquid. And so that's what that was kind of hinting at, that you would use the change in temperature to calculate the change in internal energy.
when do we?
Okay, air. So now that I think about it, if you're doing this fully as an ideal gas, you don't have to look up the enthalpy, because you can use this fact. So you can, from this equation, you can calculate the change in internal energy, and then the change in specific enthalpy is equal to the change in internal energy plus the change in pressure times specific volume. Specific volume does change for an ideal gas. And so you can, but anyways, you can use the ideal gas law to calculate specific volume at the inlet and specific volume at the exit. You're given the pressures, and so that lets you calculate that. If you used a website to do this stuff, that's perfectly fine for this weekly assignment. But It's very likely that on exams I'm going to ask you to figure stuff out just using ideal gas information. So be sure you're getting used to that too. Yep.
When do we use the C little p
Um,
constant pressure?
well, that is so CP is the partial of H with respect to um, temperature at constant pressure. And that is the partial with respect to temperature of U plus P little v. Um, and so that is, du d temperature plus P. So, okay. So let's make this substitution. PV from the ideal gas law is equal to RT. And so this is equal to the partial with respect to temperature of RT at constant pressure. And so du dt is equal to CV. This is just the total derivative with respect to temperature of RT. And so this is R. And so I guess you could use CP to integrate to calculate the specific enthalpy change. Just using this. So if you know CV and you know R, you can.
R is a constant, right?
For each gas, it's a constant. Yeah, that's right. So you have to do it for each gas. Most of the time, the problems that I give you for ideal gases are air, and that's 289 or 287 or something. Any other questions about this one? Okay, so I was intending for you to use ideal gas assumption, but I didn't say that. So of course it's totally fine to use the website. I think the thing was that before I was using that website, our tables didn't have dry air as one of the things, so you had to use ideal gas, but it's not a big deal. But for the exams, get ready to use ideal gas assumptions and incompressible assumptions.
And for this example, it would make sense that it would be like negative. Would we want to create the absolute value based on how it was asking the question, like not saying like negative 500 kilowatts or it's 500 kilowatts at this hour? What would we want to provide?
What's the electric power? Either one is fine. But yes, you are right that power would be coming into the system, so your W dot would be negative.
Still going into the system, not affecting the surroundings, right?
Yeah.
So that would make it
right. Yeah.
So
if I think the easiest way to think of it is if the system is gaining energy from work, it's negative. If the system is losing energy from work, it's positive.
And it would be more than the heat loss because there's still
Yeah.
greater than the 500
Yeah.
kilowatts from that heat loss.
Yeah.
There's still energy being.
Yeah, right. Any other questions?
One of them was from the assignment from, was it part 2 of the last assignment?
Okay.
It was for for the pump, use the assumptions from the lectures instead of going across first law, where I just went directly to work is equal to the m dot W dot equal to m dot times the difference of g.
It's this one,
Yeah, yeah, number 4.
number 4. Okay, do you want me to go through it?
I was just wondering if the assumption was still valid, since I got rid of the end, the velocity.
I don't know. I don't remember how to do this problem, so I would have to either do it or not do it, kind of.
In that case, yeah.
Okay. Okay, great.
Oh, I also converted everything into metric again, rather than
Yeah.
just dealing with the pounds force.
Yep.
But like if it's a pump and it doesn't say like what at the outlet, it just says that outlet's 40 feet above.
Mm-hmm.
If unless it's like different conditions, can we assume that it doesn't change if it doesn't give us
Yeah.
an enthalpy change thing?
Yes. Yes. So, right, you're assuming that the atmospheric pressure and temperature are the same because it's both just outside. Yes.
It also gave us the inlet velocity, about 40 feet per second, and didn't specify that there was a change in velocity. Can we just assume that velocity inlet and exit are equal and therefore can be taken out of the first law?
Well, so I guess what you probably want to do there is we're trying to figure out the minimum power required to get this fluid from the bottom up to the top. So you can assume that the speed is 0 at the, it would take more power to have it going 40 feet per second when it gets to that height. Okay, so yeah, these are crazy units. Do you have the conversions in front of you, Marco?
Yeah, it was pressure inlet 40.7 pounds per force is converts to.
Okay, wait. Pressure at the inlet is what? 40.7?
No, that was its original unit. It was I turned it into 101.4 kilopascals,
Oh, okay.
and the inlet temperature was just 17.8 degrees Celsius, and velocity of the inlet was 12.2 meters per second, and what was it? The volumetric flow rate was 1.3 times 10 to the negative 3 meters cubed per second.
Okay, tell me that one again.
1.3 meters cubed per second. It was originally 20 gallons per minute, which makes sense. It would be so small as meters cubed. It would be greater than a gallon, and seconds are a lot smaller than minutes.
Okay, and this is liquid water. So
1.3 times 10 to the negative 3.
and then okay, we're assuming that the pressure and temperature are the same at the exit. Okay, so let's start. This is steadily, so this is steady state. So we have 0 is equal to Q dot minus W dot plus M dot times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. Since this is liquid water, we can assume that the density is 1,000 kilograms per cubic meter. You also could look up the specific volume at those conditions.
That's
And
kind of what I did. I got roughly.
yeah, that's fine. It's basically the same.
99
Yeah.
998.
Yeah.
It's like
The same, right.
kilograms off.
Right. So I can I'm going to change. So we know the change in height. 40
It's the same.
40 feet is
velocity.
what?
It's the same magnitude as the velocity since it was same.
What's 40? Oh, yeah, I got you. Yep. So we're going to call ZE 12.2 meters. And we're ignoring heat transfer. We are assuming the conditions are the same at the inlet and the exit, so those enthalpies are going to go away. And so W dot for the control volume is equal to, oh, I was going to use this to get the mass flow rate. So M dot is equal to 1,000 times 1.3 times 10 to the minus 3, which is 1.3 kilograms per second. So this is equal to 1.3 times the quantity. At the inlet, we have 12.2. So that's squared over 2. Minus 1.3 times the quantity. We're going to assume that the speed is 0, but this is 9.8 times 12.2 meters. And now you have all the numbers, and you can just plug that in and get the work rate.
I think my answer was off because I just assumed that the velocities were the same, but it's not. That wouldn't
Okay.
got minimum energy. So,
Yeah.
well, it was the same other than that.
So
And-
why is velocity not the same?
Well, so it would take more power in a pump so if you want to lift water 40 feet, it would take more energy if you want it to be at 40 feet and 40 feet per second of speed, So this is saying, like, what's the required power? Like, what's the least power that this thing could require in order to get water up to that height? It's going to be a smaller amount of power if you don't assume that it's moving,
Originally, my answer was like negative 150 watts.
So,
this comes out to like negative 58 watts. Big difference.
So it enters at 12.2 meters per second and then exits at basically like negligible?
Yeah.
Okay.
Because that's the minimum. You know what I mean?
Okay.
That's the minimum power that you would have to apply to that pump, Any other homework questions? I guess let's go back to the, let's just make sure we finish this outline today. So back to the outline of topics so far. And what we finished at the end of class last time was we finished the differential form of the first law, including the heat transfer equations. So now we're moving on to part 3, which is material property relationships. And you can think of this as relationships between properties at a single state. And so the first thing I talked about was the PVT surface. And I showed you some sort of three-dimensional looking pictures of the surface, but we're really not going to use the surface for anything. The thing that's useful to us are the two-dimensional projections of the surface. The key feature is the vapor dome. And it shows up in some way or another in basically every projection. And the interpretation is the top is the critical point. The bottom is the triple line. That's where all three phases exist in equilibrium. And then what's really important to us is these two boundaries. The green boundary represents a saturated liquid. The red boundary represents a saturated vapor. And inside the vapor dome is a mix of liquid and vapor. So when you talk about quality, you're only talking about materials that are inside the vapor dome. Over on this side is a compressed liquid. And over on this side is a superheated vapor. And we talked about quality. Remember that quality is only relevant at saturation. Maybe I'll say at saturation conditions. We represent the quality with the variable x and define it as the mass that's vapor divided by the total mass, or the mass that's vapor plus the mass that's liquid. And it's between 0 and 1. A quality of 0 is a saturated liquid. A quality of 1 is a saturated vapor. So that green line on the left of the vapor dome is a saturated liquid, has a quality of 0, and the red line on the right side of the vapor dome has a quality of 1. Once you know the quality, you can use it um, to find any property for the mixture. Using the formula Q is equal to um, the quality times Q for the saturated vapor plus the quantity 1 minus quality times the property for the saturated liquid. So this is where this Q represents any property. Um, we'll also do things where you sort of use this equation in reverse, like we're given what the property is for the mixture, the total property, um, and then we'll be able to solve for the quality that way. And then you can use that quality for other properties. Part C is enthalpy. The extensive enthalpy is equal to the extensive internal energy plus the pressure times the extensive volume. The specific enthalpy is the extensive divided by the mass, and you can also calculate that as specific internal energy plus P times specific volume. Then we introduced the specific heats. The definitions, you don't have to remember these, but they're defined in terms of partial derivatives. CV is equal to the partial of specific internal energy with respect to temperature, evaluated at a constant volume. And CP is the partial of the specific enthalpy with respect to the temperature, evaluated at constant pressure. And then we use the specific heats for part E, which is our simplified material models. And there are two of those. The first one is incompressible materials. For us, we're just using that for liquids. And there are three big assumptions that come from this model. The first you can think of as like the definition that says the specific volume is a constant. Even though we're assuming this is constant inside our calculations, for the best results, look this up for your temperature range in a saturation table or a website. because it does vary a little bit with temperature. The second assumption that we're going to make is that the specific internal energy is only a function of temperature. And then from that assumption, I guess from both of these two assumptions, we get that CV and CP are the same thing. We'll just call it C for an incompressible material. And it's equal to du dt temperature, the total derivative of specific internal energy with respect to temperature. And the usefulness of this is that we can come up with a relationship between a change in temperature and a change in specific internal energy. So if you separate this and integrate it, you get that the change in specific internal energy is equal to C times the change in temperature. And then the second simplified material model is ideal gases. We're going to make this assumption when the temperature is not too close to absolute zero. And the pressure is not too high. And we really have, I have 4 results listed for this one. The first one is the ideal gas law. So P times specific volume is equal to capital R times the temperature. And remember that the R that we're using there is the universal gas constant divided by the mass per mole. So this is specific to a particular gas. Then just like, so remember that this is true for both of these two simplified models. The specific internal energy is only a function of temperature. And then the specific heat thing, there is a simplified thing that happens with the specific heats, but it's not the same thing that happens with incompressible materials. We get that CV is equal to the total derivative of specific internal energy with respect to temperature, which does give us a way to calculate a relationship between a change in specific internal energy and temperature if you have a small temperature range. Anyone remember why this basically always works for liquids, but we have to be more careful about using? It just basically has to do with the shape of that specific heat if you graph it versus temperature. For a liquid, the specific heat is pretty constant as the temperature changes. For a gas, if you graph CV versus temperature, you get a pretty major nonlinear shape, you know. Um, and so this only works for pretty small parts of that graph, you know. I mentioned before, we haven't done it this way in this class, but you might think, you know, I say that that's the problem, is that CV varies a lot as temperature varies. Um, you might think, well, okay, maybe we can curve fit some nonlinear, like a polynomial or something, CV as a function of temperature. And you totally can do that. And on a lot of tables, you can actually find coefficients of a, what do they call it, a quintic, a five fifth degree polynomial, so that you can use this relationship, but it gets a little uglier because you have a polynomial instead of a constant. And then what about CP? Well, CP for ideal gases is not equal to CV. CP is equal to CV plus that specific R value of your gas. And okay, I guess I set this up with a third simplified material model that is polytropic processes. And the form of this usually is pressure times the extensive volume to some exponent is equal to a constant. So I'll just call that C. And so this lets you, if you rearrange this, once you find that constant C, you can calculate pressure as a function of volume as C times V to the negative R. And so this lets you calculate the work of expansion. And then, so this, all of what we talked about here was part 3. So now we're going on to part 4. And that is using tables and websites. At saturation, you need one property to look up the others. If you're not at saturation, you need two properties to look up the others. And then we did this one little, I guess I'll call this the one little subsection, is interpolation. With the website, you don't need this at all. If you're using the tables, you need to use this. And the interpolation equation said f of x is approximated by f of x1 plus f of x2 minus f of x1 divided by x2 minus x1, bless you, and then times the quantity x minus x1.
Professor?
Yeah.
So like when it says at saturation we need one property, is that like one general property and quality?
Yeah, right. So that's the way they do it on the website. Is it's like quality is a second property. And so you only need one application of this if you're at saturation. If you're not at saturation, you need to do this 3 times. So let's say 3 applications are needed. I'm not emphasizing this anymore in this class. So that's a historical fact for you. And then part 5 is control volumes. And there were 2 equations that we talked about so far for control volumes. The first one is the mass balance equation. And it says dm dt for the control volume is equal to m dot at the inlet minus m dot at the exit. And there are a couple of things that are useful with this. The first one is if you're at steady state, then there's no change over time in the mass in the control volume. And so that results in m dot at the inlet being equal to m dot at the exit, and you can just call it m dot. So the mass balance there is part of that steady state assumption when we go to the first law. And then the second thing that's useful is that m dot at the inlet or the exit is equal to the area times the speed divided by the specific volume. It gets a little confusing with so many V's, but this is the speed. And then second is the first law for control volumes. And I'm just going to write out the whole form here. So this is equal to dE dt, or it says dE dt, the control volume, is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE. And we talked about kind of 3 categories of things. The first one was nozzles and diffusers. I'm almost done. So speaking roughly, these exchange enthalpy change for fluid speed change. Then we talked about turbines. Um, and roughly speaking, these exchange enthalpy change for power output. And then we talked about pumps and compressors. Um, pumps are for liquids, compressors are for gases. For both of these can exchange power input for enthalpy change. And then pumps can also be used to exchange power input for height change. Okay, so that's it for the outline, and we're going to get into the second law of thermodynamics next time. Goodbye.